Hello everyone, welcome to my presentation. My name is Osama Abdurrahman. I'm a master's student in the Civil Engineering Department at Concordia University. First of all, I would like to thank co-author of this project, Dr. Ahmed Sulaiman, for his support. My presentation going to discuss the effect of mortar consistency of microencapsulated phase change material stability. This is our outline for this presentation. First, I'm going to talk about the introduction and literature review for our research project, and then we're going to discuss our objective, and after that we're going to discuss our results and conclusion. So, as we know, energy is a driving force of the economy and all daily life activities. Energy consumption has become one of the challenging dilemmas the world faces now, with the endless growing economy and the uprising technology. As we all know, the energy demand is always rising, along with the limited energy resources. There is more significant environmental impacts which put more effort to discover an alternative source of fossil fuel. According to the International Energy Agency, the building sector consumes around 30% of the total energy consumption and contribute to 30% of the total carbon dioxide emission. This attributed to the high level of standard in terms of cooling and heating. Thus, there is a need to increase energy efficient for buildings. So building energy consumption can be reduced by 30 to 50% by integrating thermal efficiency technology. There are different approaches that are available through insulation method, smart system, and building material. And there's always researchers are working to implement more new thermal system to conserve building energy. Many researchers now started to examine the potential of adding phase change material into the cementitious material to improve the thermal properties. Phase change material are smart and responsive material that change their state at the surrounding temperature change. To explain more about the phase change material and how it works, if the temperature with the surrounding increase, PCM, which is phase change material, converted from solid to liquid and started to absorb heat into an endothermic process. However, if the temperature goes down, phase change material converted from liquid to solid state and release the stored heat into an exothermic process. Phase change material can be organic or inorganic or athiotic mixture. Among these categories, paraffin PCM is commonly used in the construction application. This is due to their low price, wide melting temperature range, and because they are chemically inert, as well as they are good thermal storage density. There is several incorporation method for the PCM, phase change material, including microencapsulation, macroencapsulation, shape stabilizer, and impregnation. Phase change material were successfully incorporated into construction material such as cement, mortar, and concrete, wall board, and roofs. As you can see in the picture, phase change material can be used in hollow blocks, slabs, or in masonry brick wall. However, One of the main drawbacks of adding phase-changing material to concrete is reducing the mechanical properties induced by paraffin leakage and voids induced by broken phase-changing materials capsule during mixing. To reduce leakage and prevent direct contact with construction material, we use the microencapsulation. Also, we used self-compacting mortar to lower yield stresses and reduce the risk of fracturing the capsules. Our objective for this research is to increase the thermal storage for buildings by incorporating phase change material, and also investigating the influence of the microencapsulated phase change material content on the fresh and hardened properties of the self-compacted mortar. In our research, we use the microencapsulated with a very small particle size, 3 micron. We used it as in the self-compacted mortar as a replacement of sand with percentage 3, 6, and up to 12%. For our result, we measured the flowability for our mix. All self-compacted mortar was in the recommended range between 250 and 300 millimeter. Besides, they maintained a flow time in the recommended range as well, between 2 and 10 seconds. As you can see in this table, in general, the viscosity was enhanced by increasing the percentage of the phase change material. For instance, for the B12 mixture, the viscosity was increased by 70% when the phase change material percentage increased from 0 up to 12%. For the compressive strength, the compressive strength was executed to evaluate the mechanical properties while incorporating the phase change material. Generally, as you can see in this graph, the dosage affected the mechanical properties of the self-compacted. At age 28, mixture while incorporating 3% of microencapsulated phase change material reported a similar compressive strength, as you see here, to the control mix. On the other hand, incorporating 6% of microencapsulated phase change material resulted in a reduction in the compressive strength, which was around 10%, and increasing the percentage of phase change material up to 12%, there resulted a reduction for around 15% in the compressive strength. Finally, we got a very interesting point in our research by measuring the heat flux for our samples. At age 28, the temperature of the chamber was 35 degrees, was maintained at 35 degrees for 9 hours. Then cooling down at ambient temperature at ambient temperature at temperature around 23 degrees. As you can see in this figure, generally, like increasing the percentage of phase change material significantly increased the heat capacity and the mortar heat flux. When the temperature of the chamber is above the phase transition temperature, the microencapsulated phase change material incorporated in our sample started to absorb the heat, as you see in this figure, through an endothermic process for the first 5 hours. And during the cooling down period, an exothermic process took place, and phase change material started to release the absorbed heat over the next 9 hours. So from this experiment, we can it shows that incorporating phase change material can significantly improve the thermal performance for our mortar. So based on the result, it can be concluded that increasing the percentage of the phase change material increase the viscosity of the self-compacted mortar, and also incorporating phase change material significantly improve the thermal properties and the thermal performance of our mortar. And finally, incorporating phase change material up to 3% doesn't affect the mechanical properties. However, increasing the percentage of phase change material or mortar more than that started to reduce the compressive strengths. Thank you for listening. I'll be happy to answer any question.